shoot for speed. Now we're going to talk about competition strategies. So there are 3 layers that I would like us to think about. Going from bottom up, you have an offline environment where you do batch processing. And the nature of batch processing is that systems are optimized for throughput. This is where you can consume large amounts of data. And this is where you can do probably your historical event analysis as well. One thing I want to mention about events is when you start capturing data as events, like we just talked about in previous slide, not overwriting your data but capturing as events means every single change that you saw in the data, you're capturing every single change. This becomes a very powerful tool for analysts because now you can give them point-in-time capability. Point-in-time capability means that it sort of like works like a time machine on data. Your analyst can ask a question to your system that how did a certain user state look like at a given time in the past. For example, how many email addresses this user had registered with us 3 months ago, right? Because you have captured data in as events and have captured every single change coming into the system, you could answer the question now. And with new emerging technologies that we have these days, capturing every single change is not a big deal. It was, people would roll their eyes if you're trying to do this 4, 5, 6 years ago. But as time goes by, storage is coming cheaper. We are getting very high computation powers at cheaper price. So yes, we are able to consume this data, and it's not so expensive to keep this data in the storage as well. Now, the next upper layer is the near real-time processing. So from offline processing, you build some insights, you build some offline variables. These are normally your predictive analysis, historical analysis, very rich set of variables. But then there are some variables that you need to compute, some data that you need to analyze as events are flowing into your system. The nature of events is that event is something that has already happened, right? So normally event-driven systems are asynchronous systems. So what that really means is the user has already clicked on something, and after that event has been emitted out, and now we are getting a chance to analyze that event asynchronously. So for that fact, just that matter, it's a near real-time processing, not the real-time processing. This is where you would use technologies like complex event processing, and we'll talk more about that in coming slides. The data that you want to analyze here is very short time windows, normally hours, and this is where you shoot for high efficiency and scalability because the number of events coming into your system can significantly grow. Because if you're monitoring every single change, because there's a difference in real time and near real time. The real time processing is normally the transactions that are happening in your system, right? But in near real time, we are monitoring, observing a lot of stuff. There's a transactional data that's coming in. There's an observational data that's coming in, operational data that's coming in. So here you want to shoot for efficiency and scalability, and there are challenges around scalability. I'll share that with you in coming slides. Then there's a layer on the top, which is real-time processing. This is where we want to shoot for optimal speed, the ultimate speed. The SLAs, response time SLAs are very stringent. This is where we need to achieve high availability of the system as well. Um, the computation that you want to do in real time has to be very simple, and this is not the place where you want to shoot for accuracy, because accuracy really means analyzing large amounts of data. Only then you can make accurate decisions. So in order to achieve accuracy, you rely on your underlying layers. You rely on your offline variables plus online variables, and here you're just looking at what's coming in the context of my request. And computations here are really transient, they're short-lived for the lifetime of the user sessions. Generally, you don't feed this data into your downstream layers. You normally consume data from downstream layers. So that's our, so we talked about our data strategy, we talked about our computation strategy. Now let's look into the systems, offline systems and online systems and their ecosystems, and I'll talk about some aspects, the key learnings from here, and in certain cases the talent that's required to build these kind of systems. So offline system, I'm going to specifically talk more about Hadoop technology stack and a little bit about the data warehouses as well. So the very first thing you want to do with the offline system is think about where is my data is going to come from, because once you start recognizing where the data is going to come from, it's going to lay out the requirements for you, for the capacity requirements, what kind of processing I need to do, how I'm going to integrate this data and so forth. So there's generally in the industry we talk about two types of data structures, structured data, data and unstructured data. The key learning is when you're dealing with unstructured data, try to use systems that don't require you to have understanding of your data. For example, there are two data integration technologies that I want to talk about. One is our classic ETL processes, ETL technologies. ETL stands for extract, transform, and load. Extract means you're extracting data out of some data source, then you're doing some transformations. The fact that you're doing some transformations on data is that you have understood your data, right? Then after that you load the data into other system. So with unstructured data, the whole point is that we haven't understood our data yet. That's why it's unstructured. If we have understanding of their data, then we can lay out schemas for it, right? So the principle that you want to use with unstructured data is get the data as fast as you can into the system and let the data processing layer take care of transformation. So for this, we normally rely on Flume and Scoop. These are both open source tools. The data storage, generally for unstructured data, you want to dump it into HDFS. Then you also have HBase. This is normally where you would bring in your structured data. HDFS very good for unstructured data. So I won't go over every single box in this diagram. But another thing I want to talk about in Hadoop technology stack is scheduling and coordinations. This is a weak point in this technology stack. There are two main pain points with this area. Number one is generally when you start building Hadoop type of clusters, you can't really do a capacity planning in fine grain. You can do coarse grain capacity planning. What that means is you generally bring in over capacity. If you need 100 nodes, you might want to have 150 nodes. Why is that? Because as of today, with mostly open source technologies, Hadoop stacks, there's no there's not sufficient quality of service tools out there. What that means is there could be 2 Hadoop jobs running. There's no way to guarantee which Hadoop job should take priority over other. Um, so for that perspective, you want to have a buffer in your capacity. Another thing that's really lacking in Hadoop technology stack is the aspect of elasticity, because if you have large infrastructure, if you're not using it all the time, it would be ideal to give away that piece of infrastructure for other processing and borrow it when you need it. So these are 2 actually drawbacks that in this technology stack. Other than that, the power it brings is worth it. Now, we talked about offline system, which is data in use. Let's talk about when big data is in motion. One thing I want to lay out before talking about big data in motion is a lot of times when you talk to people, we kind of draw a boundary on big data into like offline systems. Big data is not only offline system. Big data is all of your data is big data. So either it's in motion or it's in use, it is big data, right? So for big data in motion, there's a complex event processing technology that you could leverage. The basic idea is that you feed in these event streams into processors where you can do correlation of events. What that means is you could say if user just logged in and then user clicked on show items page, then I know this user is going to, what is this user going to do next? The idea is that you're, with CEP type of technology, you're always looking forward. What is user about to do based on the events I have seen? So you're always observing the present and trying to predict the future. Whereas on offline systems, you're always looking back the historical behavior and then try to predict what's going to happen. So in complex event processing, generally events come in where they get filtered, aggregated, and so forth, and then you emit decisions out which can be consumed by your decision services. One of the principles in complex event processing is that you don't try to persist or keep those events, mean the historical events for historical lookups. It's like if you're dealing with the event, you looked at it, you just throw it away in the context of CEP system and do something, get some insight from the event, and maybe based on that insight you may generate another event. And we'll take a look at an example in the coming slide. Generally, these technologies rely on in-memory data stores to operate that fast. Because like we talked about before in a couple of slides before, this is where you want to shoot for efficiency and scalability. The speed will only, you can't really rely on persistent data stores to build CEP systems. People who have tried this, the systems have failed. Or if you know of systems that are working based on persistent data stores, they might be very small scale systems, but when the scale goes up, then disk I/O can't really keep up with that kind of volume. So out of CEP system, you're storing some data in in-memory data store, you're sending events to decision service. At the same time, you could send alerts or some observational data, means how my logic is performing in the system or what decisions I made, asynchronously to message bus, which can be consumed by offline systems. So in a way, what you're doing is you're building a feedback loop. Your complex event processing is notifying offline system that this is what I did. Then on offline system, you run a bad job at some product period and do analysis on what was done by complex event processing and feed the data back into complex event processing. For example, you could be running some sort of model here and say this is how my model is behaving, and offline system can say, okay, my model performance is degrading, hence I need to tune my model by adjusting some parameters and then send the data back into the real-time system. So that's how you can combine both online and offline technologies. So one thing with complex event processing is the scalability challenges.